planet may not be as alone in space as once believed. For decades, whispers within the scientific community have hinted at the presence of mysterious structures, not celestial bodies in the traditional sense, but vast, ghostly forms said to share Earth's orbit. These entities are not recognized moons or passing comets, yet their presence is rumored to loom in the gravitational shadows of our planet. Some reports describe them as immense and diffuse, stretching across regions of space up to 9 times wider than Earth itself. Faint and fleeting, they appear in some observations as hazy silhouettes suspended in stillness. Yet when others have scanned the same regions, the sky reveals nothing at all. No consistent shape, no measurable mass, only speculation. For more than 60 years, astronomers have debated their existence. Are these anomalies merely tricks of light and atmosphere? Or are they real, persistent features, cosmic phenomena that have somehow evaded the full scrutiny of modern science? The question remains unsettling. Is Earth truly accompanied by only one moon? The mystery traces back to 1961, when Polish astronomer Kazimierz Kordylewski reported observing 2 pale, cloud-like structures near specific positions in space known as Lagrange points, zones of gravitational balance created by the interaction between Earth and the Moon. These zones, labeled L4 and L5, form equilateral triangles with the Earth and the Moon, allowing objects to remain relatively stationary within them. Lagrange points are not imaginary coordinates. They are real locations where the gravitational pull of 2 massive bodies, in this case, Earth and the Moon, combines with the motion of a smaller object to create a stable environment. In such places, material can theoretically accumulate and linger, held in a quiet equilibrium. Kordylewski's observations suggested that dust, gas, or some unknown form of matter had settled into these points, not as solid moons, but as vast, semi-transparent clouds. Though largely dismissed at the time as observational error or atmospheric interference, his findings have remained a curiosity, revisited over the decades with more advanced instruments. Still, the mystery persists. Some studies claim to have detected faint traces of these so-called ghost moons, while others report no such evidence. The debate continues, hovering between astrophysical theory and the edges of observable science. In a universe governed by mass, motion, and gravity, how can something so large remain so difficult to see? Perhaps the answer lies not in what is seen, but in what is overlooked, in the thin veil between darkness and light, where the known laws of physics allow strange things to quietly exist. The investigation continues, not only into what may orbit alongside us, but into the very limits of our perception of the cosmos. The concept of Lagrange points, now central to many space missions, was first formally described in the 18th century by the mathematician Joseph Louis Lagrange. These unique regions in space exist within 2 body systems, such as Earth and the Moon, or Earth and the Sun. At these 5 positions, labeled L1 through L5, the combined gravitational pull of the 2 larger bodies balances the motion of a smaller object, allowing it to remain relatively fixed in space. In any such gravitational system, 3 of these points, L1, L2, and L3, are considered unstable. Though spacecraft like SOHO and the James Webb Space Telescope are positioned near these zones, they require regular adjustments to maintain their positions. Even slight influences, such as solar wind or gravitational nudges, can push them off course. By contrast, L4 and L5 are known for their relative stability. These points form equilateral triangles with the Earth and the Moon, and are less susceptible to gravitational disturbances. As a result, they have become areas of particular interest. Over time, particles of dust, or even small asteroids, can become trapped there, lingering for years or even centuries. It was near these stable points that Kazimierz Kordylewski reported observing two faint, cloud-like formations in 1961. Initially dubbed libration clouds, they would later be named Kordylewski dust clouds (KDCS) in his honor. His claims sparked intrigue, but also skepticism. Despite repeated attempts by other astronomers to verify the sightings, the clouds often eluded detection. Technological limitations at the time played a major role in the uncertainty. The faintness of the supposed clouds made them exceptionally difficult to observe, especially from ground-based telescopes operating in light-polluted environments. The methods used involved long-exposure photographs on glass plates, designed to detect minute changes in light intensity, not to capture sharp, visual images. These early photos, including some taken by Kordylewski himself, were too dim to be printed in mainstream publications. Nonetheless, they showed subtle variations in light that hinted at the presence of something more than empty space. A major milestone came in 1966, when NASA launched an airborne observation campaign using a high-altitude laboratory aircraft. At over 12,000 meters above the Earth, far from atmospheric interference, the team managed to photograph the dust cloud located at the L5 point. The same year, the OSO-6 satellite reported similar observations. Despite this progress, consensus remained elusive. A decade later, in 1976, Siegfried Röser of the Max Planck Institute conducted simulations suggesting that dust should not be able to persist at L4 due to destabilizing influences such as the solar wind and planetary perturbations. His findings reinforced doubts already growing within the scientific community. Additional radar studies around the same period yielded no definitive results. Many concluded that the gravitational environment was too hostile for sustained dust accumulation at either L4 or L5. Observations in 1983 using a telescope in Arizona also failed to detect the clouds, strengthening the skepticism. Yet the mystery would not fade. In 1989, Maciej Winarski conducted a new series of observations from the Bieszczady Mountains in Poland. Not only did he confirm the presence of the clouds, but he also achieved the first three-color photometric analysis. The results were striking. The dust clouds appeared significantly redder than the general background dust that reflects sunlight in space, known as the counterglow. This suggested that the material within the KDCS was compositionally distinct from surrounding interplanetary dust. Such a finding raised new questions. If these clouds truly existed, and if their composition was unlike anything else nearby, where did they come from? What mechanisms allowed them to form and persist in such an unstable environment? In 1991, hope for a definitive answer was once again challenged. The Japanese Heightened Space Probe executed a pass through the L4 and L5 regions in an attempt to detect dust particles. It found nothing, but scientists cautioned against drawing firm conclusions. Heighten's trajectory allowed only a single loop around each point, and its sensors were not optimized for detecting slow-moving dust. If the particles were present but drifting too gently, they may have slipped through the probe's detection systems unnoticed. The investigation into the Kordylewski dust clouds continues to this day. The search represents more than a curiosity. It is a case study in the limitations of observational science, a reminder that even in a space age defined by precision instruments and global networks of telescopes, there are still corners of our immediate cosmic neighborhood that remain cloaked in mystery. The debate that began in 1961 with Kordylewski's initial report has never fully subsided. For decades, astronomers have questioned whether his sightings were legitimate or merely artifacts of imperfect observation. But recent developments suggest that the mystery may be closer to resolution. In 2018 and 2019, a significant breakthrough occurred. Using advanced optical techniques, a team of researchers led by astronomer Judith Sliss-Belloc alongside physicists Gabor Horváth and András Barta, presented compelling new evidence supporting the existence of the Kordylewski dust cloud at the L5 Lagrange point. The team employed a sophisticated method known as polarized imaging, a form of photography that utilizes specialized filters to isolate light scattered at specific angles. When sunlight interacts with dust particles in space, it scatters in distinctive ways, depending on the shape, size, and composition of those particles. By analyzing the patterns of this polarized light, scientists can infer the presence and nature of the scattering material. After collecting a sequence of images using various polarized filters, the team discovered patterns of scattered light that closely matched theoretical predictions. The data indicated that the light could only be explained by interaction with fine dust particles, a conclusion that aligned with long-standing hypotheses about the KDCS. Their published findings went further, stating that the scattering observed in their images cannot be anything other than dust particles. This conclusion marked one of the most definitive statements on the phenomenon in over half a century. To corroborate their observations, the researchers turned to computational modeling. Simulating the motion of over 1.8 million virtual dust particles, they explored how such matter might behave under the gravitational dynamics of the Earth-Moon system. The results were striking. Under specific conditions, the dust appeared capable of becoming trapped at the L5 point, forming persistent clouds that reflected the same dimensions and structures seen in the polarized images. These findings raised an important question. If the clouds exist and can be simulated and photographed, why have they remained so elusive to so many observers? The answer lies in the nature of the clouds themselves. Although they stretch across a region nearly 9 times the width of Earth, approximately 100,000 by 70,000 kilometers, their total mass is minuscule. The dust is spread thinly over an enormous area, making the clouds virtually invisible without precise instruments and ideal viewing conditions. Their diffuse nature, combined with interference from atmospheric conditions, background light, and the moon's own illumination, makes them notoriously difficult to detect. This rarity of observation does not disprove their existence. Instead, it reveals the limits of human perception and the challenges of studying phenomena at the edge of detectability. As technology advances and new methods of analysis emerge, the possibility of confirming these ghostly companions with greater certainty continues to grow. The dust particles thought to make up the Kordylewski clouds are vanishingly small. Polarized imaging of the L5 region suggests that many are no larger than a micron or even smaller. A micron, 1/1,000,000th of a meter, is the approximate size of a single bacterial cell. Individual particles of this scale are invisible to the naked eye, detectable only with the aid of powerful microscopes or specialized astronomical instruments. This extreme smallness is compounded by the cloud's vast spatial distribution. These submicron dust particles are spread thinly across tens of thousands of kilometers, forming an ethereal, almost imperceptible veil in space. But scale and transparency are not the only challenges to observation. Recent simulations by Balog and Horváth suggest that the cloud's shape is not fixed, it is dynamic, constantly shifting in form and density. Their models indicate that the L5 cloud exhibits non-uniformity, with denser regions emerging and fading over time. These fluctuations appear to be linked to the Moon's orbit, suggesting a cyclical behavior driven by gravitational interactions. Rather than a static accumulation of particles, the KDCS may behave more like a diffuse, ongoing dust storm, a system in continuous transformation, losing and regaining matter as it orbits in tandem with the Earth and Moon. This instability is likely influenced by external forces: the solar wind, the gravitational tug of other planets, and variations in sunlight can disturb the delicate balance that sustains these dust clouds. In this view, The Kordylewski clouds are not permanent structures, but transient phenomena dispersing, reassembling, and vanishing depending on conditions in their orbital environment. Such characteristics help explain the erratic nature of past observations. A cloud may be present and detectable one year, only to dissolve or thin beyond visibility the next. These inconsistencies have fueled decades of debate, yet they are precisely what would be expected from a structure composed of micron-scale dust in a turbulent cosmic zone. Even with this new understanding, many questions remain. The 2018 observations provide strong evidence for the existence of the L5 dust cloud, but do not settle the matter entirely. One unresolved issue is whether the KDCS are a constant presence, or if they appear sporadically, influenced by the solar cycle or planetary alignments. What is increasingly clear is that these clouds are not imaginary. They are not illusions or misreadings of scattered starlight. The accumulating body of evidence points to a real, physical phenomenon, a subtle and delicate one, but real nonetheless. Scientists now widely agree that the Kordylewski dust clouds merit further investigation. In the broader context of Earth's orbital companions, the idea of additional moons, whether solid or cloud-like, is not without precedent. Earth has, on several occasions, hosted what are known as minimoons and quasi-moons. These objects differ significantly from the KDCS, but illustrate that our planet's gravitational field is capable of capturing a range of orbital guests. Minimoons are small natural satellites that are temporarily caught by Earth's gravity. They typically remain in orbit for a few months to a year before escaping back into space. In contrast, the Lagrange points, the gravitational traps associated with KDCS, have existed for as long as the Earth-Moon system itself. This raises the possibility that the Kordylewski phenomenon may be billions of years old. Unlike dust clouds, minimoons and quasi-moons are solid objects. Quasi-moons can appear to orbit Earth, but in reality, they travel around the Sun while maintaining a path that mimics Earth's. Minimoons, on the other hand, do enter into orbit around Earth, albeit briefly and erratically. Only a handful of minimoons have ever been confirmed. One such object was 2020 CD3, a small body that orbited Earth from early 2019 until mid-2020. Though it was too small to be observed without dedicated equipment, it was nevertheless a genuine, albeit temporary, natural satellite of our planet, a second moon in miniature. These examples, though rare, underscore a larger truth. Earth's neighborhood in space is more complex than it appears. Alongside the familiar presence of the moon, there may be unseen visitors, some solid, some ephemeral, quietly sharing our orbital path. Among the lesser-known celestial phenomena, the Kordylewski dust clouds stand out as particularly intriguing. Unlike transient objects that pass briefly through Earth's orbit, these ghostly formations may represent a semi-permanent feature of the Earth-Moon system, not fixed like the Moon, but not fleeting either. Their uniqueness lies in their nature, dynamic, diffuse, yet potentially long-lived. Studying these structures has pushed the boundaries of observational astronomy. Detecting something so faint and so vast requires not just advanced instruments, but also a deep understanding of how light interacts with matter on the smallest scales. As both technology and scientific methods advance, so too does the opportunity to better understand these elusive clouds. To date, the majority of observations have focused on the L5 point, but the L4 region remains less explored. Expanding observational efforts to both Lagrange points could reveal new insights. Modern techniques, including updated radar surveys and space-based instruments, may succeed where earlier attempts failed, potentially offering new confirmation and data on the physical characteristics of these formations. Now that the existence of the Kordylewski dust clouds has gained broader acceptance within the scientific community, researchers are turning toward the next set of questions. How are these clouds maintained over time? What are their interactions with the surrounding space environment? Could they play a role in space weather or subtly affect satellite operations and orbital debris? Whether these clouds are persistent or periodically reformed by shifting cosmic forces remains under study. But what is clear is that something is indeed present, not just a theoretical construct, but a real phenomenon that merits focused scientific attention. The Kordylewski clouds remind us that the cosmos still holds surprises close to home. Even in the familiar orbit between Earth and Moon, there are mysteries soft, spectral veils that challenge what we thought we knew. They are a testament to the fact that discovery is not confined to distant galaxies. Sometimes, the most fascinating enigmas are those that drift just overhead, quiet, persistent, and waiting to be understood. The rediscovery and ongoing investigation of the Kordylewski dust clouds offer more than just a deeper understanding of Earth's orbital neighborhood. They provide a rare opportunity to reflect on the evolving nature of scientific observation itself, a process shaped by the interplay between curiosity, skepticism, and the slow unfolding of technological capability. What began as a set of faint anomalies glimpsed through the lens of mid-20th century telescopes has now transformed into a legitimate area of research, with implications that extend far beyond atmospheric dust. One of the most compelling aspects of these ghost clouds is their challenge to traditional notions of what constitutes a moon. For centuries, the moon stood alone as Earth's only natural satellite. Yet, discoveries in the last few decades of quasi-moons, temporary minimoons, and now dust-based orbital structures suggest that the idea of a moon may need to be reconsidered. If a structure is gravitationally bound to a planet, interacts with its orbital mechanics, and can persist over time, does it not, in some form, qualify as a companion? While the KDCS differ significantly from solid objects lacking mass concentration, gravity of their own, or a fixed core, they still occupy stable orbital regions, respond to cosmic forces, and exhibit a kind of structural persistence. In this sense, they represent a new class of celestial companion. Neither moon nor ring, but a third category altogether diffuse, evolving, and difficult to classify. This ambiguity is precisely what makes them scientifically valuable. They allow researchers to study gravitational equilibrium in action. At Lagrange points like L4 and L5, the push and pull between Earth and the Moon is so perfectly balanced that even the slightest additional force, solar radiation, space debris, micrometeorite impacts can make a measurable difference. The KDCS serve as living laboratories for understanding these forces, helping scientists model not just our own orbital system, but similar zones throughout the solar system and beyond. The insights gleaned from studying these dust clouds could also have practical applications. As space travel becomes more frequent and Earth orbit grows increasingly crowded, knowing where regions of dust accumulation exist becomes vital for the planning of long-term missions and satellite deployment. While the KDCS pose no immediate threat to spacecraft, their presence may influence orbital stability in subtle ways. A better understanding of their composition and behavior could inform the design of navigation systems, particularly for vehicles operating near Earth-Moon Lagrange points. There are also speculative, but not implausible applications for space resource management. If these dust clouds contain particular mineral compositions distinct from background cosmic dust, future missions might aim to collect and analyze their particles in greater detail. Such missions could also clarify whether the material is of lunar origin, dislodged by ancient impacts on the Moon, or if it stems from more distant sources, such as passing comets or interplanetary collisions. In addition to their scientific utility, the Kordylewski clouds challenge deeper assumptions about visibility, presence, and reality. For centuries, astronomy has relied on the ability to observe and measure light stars that shine. planets that reflect, and galaxies that burn with distant fire. Yet here are structures that exist almost entirely in shadow. They do not emit light. They do not reflect it strongly. They do not announce themselves through gravity or magnetism. Their presence is detectable only through the most subtle of interactions. The way light scatters as it brushes past particles, no larger than a bacterium. In this way, the KDCS echoes certain principles found in quantum mechanics phenomena that exist only in the margins, understood not through direct contact, but by inference. Their existence invites a broader philosophical question. How much of the universe might operate beyond the reach of our current methods of detection? And what else, like these clouds, might be waiting to emerge once the right instruments or the right questions are applied? This reflective dimension is not just poetic. It has real-world implications. In an era increasingly reliant on data, prediction, and visibility, the Kordylewski clouds stand as a reminder that not all truths are immediately knowable. Some must be approached indirectly through patience and inference. They highlight the importance of scientific humility, the recognition that even near Earth space, the most familiar region of the cosmos, still contains mysteries. Looking ahead, there are many pathways for further study. One key priority is sustained observation. While several images of the L5 cloud have now been captured, the L4 region remains comparatively underexplored. Coordinated efforts between ground-based observatories, weather balloons, and orbital telescopes could yield higher fidelity data and help clarify whether both clouds are consistently present. Another promising direction lies in situ sampling. A dedicated probe, equipped with particle detectors and dust analyzers, could traverse the L4 and L5 regions, gathering real-time data on particle density, composition, and motion. Such a mission would not only confirm the cloud's material makeup, but also help determine whether they are continually replenished by lunar ejecta, interplanetary debris, or a yet unknown process. Further modeling is also essential. While simulations by Sliz Balog and Horvath have shown how dust could remain trapped under certain conditions, these models could be expanded to include variables like solar flares, coronal mass ejections, or asteroid flybys, all of which may play roles in dispersing or reshaping the clouds. Ultimately, the Kordylewski dust clouds offer a unique fusion of the concrete and the mysterious. They are grounded in gravitational dynamics, a well-understood framework, yet exhibit behavior that resists easy explanation. They challenge perception, yet invite rigorous inquiry. They straddle the line between presence and absence, revealing that even in space, the invisible can leave a trace. As scientific attention gradually turns toward these silent companions, a broader awareness is forming. Earth's orbit is not empty. It is shaped by tides of dust, swept along in the gravitational balance between planet and moon. In the shadows of this equilibrium, clouds drift fragile, quiet, and ancient. They do not shine. They do not orbit with purpose. But they endure. And in their endurance, they whisper of a cosmos more subtle and surprising than once imagined. In the ever-expanding quest to understand our universe, discoveries often arrive with great spectacle: the blaze of a supernova, the collision of galaxies, or the distant hum of gravitational waves. But not all truths reveal themselves in flashes of light or bursts of energy. Some, like the Kordylewski dust clouds, appear only in whispers, subtle, elusive, and patient. These ghostly formations remind us that the cosmos is not merely a theater of grand events, but also a realm of quiet intricacies. They show that even in the well-trodden path between Earth and Moon, there are still secrets waiting to be seen. Not by force, but by focus. Not by assumption, but by attention. Though composed of particles too small to see and too faint to measure with ease, the KDCS challenge our understanding of orbital stability, light behavior, and the very limits of observation. They exist in a space between the visible and the invisible, not entirely gone, but not fully present, and in doing so, they expand the boundaries of what we consider real. Perhaps their greatest value lies not only in what they are, but in what they represent. The frontier that still exists right above our heads. In a world where space is increasingly mapped and measured, the Kordylewski clouds remind us that the unknown is not far away. It is here, orbiting with us, quietly defying expectation. As research continues and new instruments peer into these overlooked corners of space, one truth becomes clearer. Discovery is not reserved for distant stars or alien planets. Sometimes, the next great revelation is found not light years away, but in the shadows we have yet to fully explore. In the silence of the Lagrange points, the dust still drifts, and while it may never roar, it speaks to those who are still listening.